Somewhere above the continental United States, at this very moment, one of the most sophisticated machines ever assembled by human hands is almost certainly airborne. It carries no tourists, no cargo, no ordinary passengers. Its manifest does not appear in any public database. Its flight path is classified, and yet it is always there. A silver silhouette threading through the stratosphere at 30,000 feet, sustained not just by 4 thundering jet engines, but by a nervous system of pure light, a skin of electromagnetic armor, and a brain that can survive the end of the world. This is the E-4B Nightwatch. The press calls it the Doomsday Plane. The military calls it the National Airborne Operations Center. The President of the United States and the Secretary of Defense call it their last resort. And what they built inside of it will leave you breathless. To understand why this aircraft exists, you have to understand the single most terrifying scenario that American military planners have ever been forced to prepare for: a nuclear first strike so sudden, so overwhelming, that every ground-based command center, the Pentagon, Strategic Air Command, the White House Situation Room, is gone in a flash of atomic fire before a single order can be given. In those first nightmarish minutes after a surprise attack, the chain of command cannot simply collapse. Someone, somewhere, must be able to reach the submarines lurking in the deep Atlantic, must be able to communicate with ballistic missile crews still waiting for orders in their underground silos, must be able to speak directly to foreign leaders on encrypted lines and determine whether civilization itself has any future. That someone has to be airborne, unreachable, and utterly indestructible. And so, they built the E-4B. The story begins in the early 1970s, when the United States Air Force looked at its existing command aircraft and acknowledged with characteristic military bluntness that they were woefully inadequate. The old EC-135 Looking Glass aircraft that had been keeping watch since the early 1960s were capable machines for their time, but the exponential growth of Soviet nuclear capabilities demanded something far more ambitious, something that could not just survive on the margins of a nuclear war, but operate at its epicenter. The solution was the Boeing 747, specifically the wide-body 747-200 airframe, the most capable heavy transport in the world at that moment, chosen not for its passenger comfort, but for its sheer volume, power, and range. 4 of these aircraft were converted under classified contracts. The number has not changed. There are still 4 E-4Bs in the fleet today, operated by the 1st Airborne Command and Control Squadron out of Offutt Air Force Base in Nebraska. And while the airframe itself is borrowed from the world of commercial aviation, virtually everything else about this machine is exclusive, bespoke, and jaw-droppingly complex. Begin with the exterior, because even the skin of this aircraft tells a story of extraordinary engineering paranoia. The fuselage of the E-4B is not simply aluminum and rivets. Woven throughout the aircraft structure is a comprehensive electromagnetic pulse hardening system designed to protect every circuit on board from the devastating electromagnetic shockwave that accompanies a nuclear detonation. When a nuclear weapon explodes, even at altitude, it releases a burst of gamma radiation that interacts with the atmosphere and the Earth's magnetic field to produce an electromagnetic pulse, a wave of energy capable of frying unprotected electronics across hundreds of miles instantaneously. Every transformer, every microchip, every communications relay that lacks protection simply dies. The engineers who built the E-4B understood this with the clarity of people whose jobs depended on it. And so they wrapped this aircraft in layers of shielding, grounded its critical systems, and surrounded its electronics in a protective web of Faraday cage-style enclosures that force any incoming electromagnetic pulse to find its energy dissipated harmlessly before it ever reaches the aircraft's critical hardware. The entire fuselage, in essence, becomes its own electromagnetic sanctuary. But shielding alone is not enough if you cannot communicate, and this is where the E-4B's technology becomes genuinely extraordinary, because the communication suite aboard this aircraft is not a single system. It is 15 separate, distinct communication systems layered on top of one another like the rings of a fortress wall, each one operating on a different frequency, a different principle, a different physical medium, so that if one is jammed, one is destroyed, or one simply fails, 14 others remain. The aircraft can speak on high-frequency radio, on ultra-high-frequency satellite bands, on the military's protected Milstar constellation. It can transmit compressed data packages in fractions of a second across strategic networks. It carries airborne radio relay antennas that extend its reach to forces operating where no satellite signal penetrates. And then there is the most astonishing communication system of all, the trailing wire antenna. Coiled inside a retractable drum housed in the aircraft's tail section is over 5 miles of extremely low-frequency wire antenna, a copper lifeline that, when deployed during flight, dangles beneath the aircraft like a thread, vibrating with signals of such profound low frequency that they penetrate the ocean's surface and reach nuclear submarines lurking hundreds of feet below the waves. This is not metaphor. The physics of extremely low-frequency transmission, known as ELF, allows signals to pass through seawater that would stop any higher-frequency wave cold. A submerged Ohio-class ballistic missile submarine, carrying enough nuclear warheads to rewrite the map of a continent, receives its orders not through any antenna it can raise above the surface, but through the trembling vibration of an ELF signal pulsed from this wire, dragged through the sky at 500 miles per hour, 5 miles above the Earth. That image alone, a thread of copper dancing in the jet stream, carrying the weight of nuclear deterrence, captures everything that makes the E-4B uniquely fascinating. Now comes the next generation, because the E-4B, for all its remarkable capability, is a machine of the 1970s at its foundation. Its 4 Pratt & Whitney F103 turbofan engines, while still producing staggering thrust, are aging. Its original analog systems have been progressively updated, but the patchwork of half-century-old architecture and modern digital overlays creates maintenance challenges that have grown steadily more severe. Parts for certain aircraft systems no longer exist in any catalog. Technicians sometimes fabricate replacements by hand. The Air Force has been grimly candid. The E-4B cannot fly forever.
Enter the E-4C, the next-generation National Airborne Operations Center that the United States Air Force is now developing will not simply refurbish what came before. It will reinvent it from the inside out, beginning with the most visible and immediate transformation, a completely digital glass cockpit. Where the current E-4B still relies on a constellation of analog gauges, mechanical backup instruments, and generations-old avionics displays that any museum curator would recognize, the new aircraft will present its crew with floor-to-ceiling arrays of high-resolution digital displays driven by fault-tolerant, redundant computing systems. Every instrument reading, every navigation parameter, every system status indicator will be rendered in crisp, adaptive digital formats that can be reconfigured in flight. The crew will fly not through the clutter of 100 separate dials, but through a unified, intelligent interface that aggregates the aircraft's information into coherent, prioritized streams of data. It is the difference between reading a city's traffic by driving every street individually versus watching it from orbit in a single glance. The new cockpit's computing backbone is hardened not just against electromagnetic pulses, but against cyber intrusion, another threat that simply did not exist when the E-4B was conceived. The networks on board will be air-gapped, physically separated from any external connection, with cryptographic protections so layered that unauthorized access is not merely difficult, but mathematically impractical within any time frame that the mission requires. The communications revolution goes further still. At the heart of the next-generation aircraft's communication architecture is a shift from copper wire to light. Fiber optic cabling, strands of pure glass finer than a human hair, carrying data as pulses of laser light at the speed of, well, light, will replace the copper wiring that snakes through the E-4B's aging frame. This is not merely an upgrade in speed, though the bandwidth improvement is staggering, capable of moving data at rates measured in gigabits per second, where the old system struggled to push kilobits. The real advantage of fiber optics in this context is immunity. Copper wire is sensitive to electromagnetic pulses. It acts, under certain conditions, as an antenna, exactly the wrong property for an aircraft designed to survive nuclear warfare. Fiber optic cables carry no electrical current. They cannot be induced to carry a damaging voltage spike. They are, in the most literal physical sense, immune to the electromagnetic chaos of nuclear detonation. The entire nervous system of the new aircraft will be redrawn in light rather than electricity, and the result will be a communications and data infrastructure that is simultaneously faster, more capable, and more survivable than anything the current fleet can offer. And then there are the lasers. The most classified and in many respects the most remarkable communications technology being integrated into the next generation of the Nightwatch involves laser-based communication systems that operate on principles orthogonal to everything that came before. Traditional radio communications, even the most advanced, most encrypted, most sophisticated radio systems, work by broadcasting electromagnetic waves into the atmosphere. Those waves radiate in every direction. They can be detected, analyzed, triangulated, and jammed. A powerful enough jamming signal on the right frequency can disrupt even the most protected radio system, at least partially, at least briefly. In a world where adversaries have spent billions of dollars developing electromagnetic warfare systems specifically designed to disrupt American command and control, even a brief communications blackout at the wrong moment carries existential consequences. Laser communications solve this problem at the physics level. A laser beam does not broadcast, it points. The intense, coherent light of a military-grade laser communication terminal travels in a pencil-thin corridor of directed energy that contains no appreciable side lobe radiation. It arrives only where it is aimed. It cannot be intercepted by any system that is physically positioned in the precise path of the beam. It cannot be jammed by any radio frequency jamming platform because it operates entirely outside the radio frequency spectrum. And because the data it carries is encoded in modulations of light rather than electromagnetic oscillations, it achieves data transfer rates that dwarf conventional radio systems by orders of magnitude. A laser communication link established between the E-4C and a satellite, another aircraft, or a ground terminal would be, for all practical military purposes, unjammable, undetectable from the side, and faster than any radio equivalent. The engineering challenges of maintaining a laser communication link from a moving aircraft are immense. The terminal must track its target with sub-arc-second precision, even as the aircraft bends and flexes in turbulence, even as atmospheric thermal gradients scatter and distort the beam, even as the curvature of the Earth and the speed of both endpoints constantly shift the geometry of the link. The solution lies in adaptive optics, mirror systems driven by real-time atmospheric sensing that adjust their shape hundreds of times per second to counteract distortion before it disrupts the signal. It is the same technology that allows ground-based telescopes to see stars clearly through the turbulence of Earth's atmosphere, repurposed for the most demanding communications application imaginable.
Inside the aircraft, beyond the cockpit and the communications bay, the working spaces of the next-generation Nightwatch will be transformed as completely as the systems that support them. The current E-4B carries a battle staff of up to 112 personnel: generals, intelligence officers, communications specialists, nuclear weapons employment coordinators, medical staff, security teams. Their workspaces, while functional, reflect decades of accretion, systems bolted alongside systems, displays added to displays, the organic growth of a machine that has been continuously updated without comprehensive re-architecture. The new aircraft will provide these personnel with integrated workstations, shared secure networks, and collaboration tools that allow the battle staff to function less like a collection of separate specialists and more like a single, distributed analytical organism, with information flowing freely across roles and decisions forming with the speed and clarity that a nuclear crisis demands. The power systems supporting all of this, the communications, the computing, the crew facilities, are themselves a marvel. The E-4B carries an airborne electrical power system capable of generating enormous amounts of onboard electricity, far beyond what a standard 747 requires, to feed the unceasing hunger of its communications racks and computing infrastructure. The E-4C will expand this capability further because the power demands of fiber optic amplifiers, laser terminals, phased array antennas, and hardened computing systems dwarf even the considerable appetite of its predecessor. Every kilowatt of that power is generated on board, independent of any ground infrastructure, sustained only by the 4 engines and the fuel in the wings. And about that fuel, the E-4B has a theoretical endurance, when refueled in mid-air, limited not by its tanks, but by the mechanical wear of its engines and the biological limits of its crew. With aerial refueling from KC-135 or KC-46 tankers, this aircraft can remain airborne for days. The current record for a single E-4B flight stretches to over 72 hours. The next generation aims to extend that capability, which is why every engineering decision, from the weight of the communications racks to the efficiency of the onboard power system, is made with an obsessive focus on reducing parasitic loads and extending operational endurance. Because the entire premise of this aircraft is endurance, it is not designed to strike, it carries no weapons, it is designed to survive, to remain aloft when everything below it has perished, and to continue, through its laser-like and its copper thread and its fiber-optic nervous system, to speak for a civilization that may no longer have a surface to stand on. It is the last voice, the last link, the final guarantee that even in the darkest conceivable moment, the authority of the United States government does not simply vanish into the mushroom clouds. That is a profound and terrible responsibility. And the engineers, the programmers, the systems integrators, the metallurgists, the communications physicists who pour their careers into maintaining and reimagining this aircraft carry it with a seriousness that is almost palpable. Every fiber optic strand they route, every electromagnetic seal they test, every laser terminal they calibrate is a small act of faith. Faith that the work is done well enough that it will never actually be needed, because the greatest success of the Doomsday Plane is a world in which it never has to do its job. But just in case this fragile, improbable civilization stumbles to the edge, the E-4C will be there, threading the stratosphere on invisible rails of habit and mission, its glass cockpit glowing softly in the thin, cold air, its fiber-optic nerves humming with light, its laser eyes fixed on satellites that hang motionless above a turning world. Always flying, always watching, always ready.